Okay, so we're doing a deep dive into Tuna, taming unified visual representations for native unified multimodal models.
Right.
And the mission here seems pretty clear. It's about tackling really the single biggest challenge for these multimodal AIs today, which is how do you build a model that can handle both visual understanding and generation and do both well?
Exactly. I mean, historically, these UMMs, these unified multimodal models, they've either been great at, parsing an image or great at creating one.
But rarely both from the same brain, so to speak.
Right. And the core innovation that Tuna brings to the table is achieving this perfectly unified, continuous visual representation.
So how do they actually pull that off? That unification sounds tricky.
It's a really brilliant cascaded architecture. They take a high-quality VAE encoder, specifically the WAN 2.2 VAE, and they run its output directly through a really strong pre-trained semantic encoder, SigLIP2.
So it forces the two to align really early in the process. It creates one shared feature space.
And that just simplifies the whole training landscape.
Massively, I'd imagine.
It does. You get rid of all those nasty representation format mismatches, the spatial, temporal, and channel dimension problems that force other models into these super complicated decoupled architectures. The result is just balance.
And the performance speaks for itself, right? We're talking state-of-the-art across pretty much everything.
Everything. Image and video understanding, image and video generation, even complex editing tasks, all from one model.
So what are some of the numbers?
Well, their 7 billion parameter model hits 61.2% on the MM-star benchmark, which is really tough, and it gets a 0.90 on Geneval for generation. It just consistently beats the decoupled models.
Proving that, unification isn't just possible, it's actually better.
Exactly.
Okay, let's unpack that central challenge. These native UMMs models, pre-trained on both understanding and generation, they're the goal, but they've been so hard to build.
Yeah.
What is the fundamental roadblock? Why is visual encoding so difficult?
Well, it's all about what each task actually needs. For good generation, you need a very detailed, spatially rich, latent space so you can reconstruct pixels with high fidelity. That's what VAEs give you.
Okay.
But for understanding, for robust understanding, you need semantically dense features. You need abstract, high-level concepts. And that comes from models trained with contrastive learning, like CLIP or SigLIP.
And those two types of features, they just don't speak the same language, do they?
Not at all. The old solution, which you see in models like Bagel or MoGao, is this decoupled approach. They use separate encoders for each task.
Which sounds complicated.
It is. It often requires things like mixture of experts or MoE architectures just to handle the inputs because they're so incompatible.
Wait, can you break that incompatibility down for us? Why can't you just feed both into the LLM?
Because the formats just clash. I mean, fundamentally, think of it like trying to plug a European power cord into a US socket. The standards just don't match. So the VAE features for generation might have a spatial compression of, say, 16 times. But the understanding features from SigLIP might only be compressed 8 times. The channel dimensions are also completely different. You could have 1,152 channels of semantic info versus just 16 channels for the VAE data.
So you have these two totally different streams of data trying to get through the same pipeline. It causes conflicts, and you need all this extra architecture like MoE just to translate between them.
Precisely. And that cost, that conflict, it always leads to compromises. The unified approach, which Tuna uses, it simplifies everything and it actually promotes what the authors call mutual enhancement.
Where understanding helps generation and generation helps understanding.
Exactly.
But, historically, these unified models have kind of underperformed. I'm thinking of models like Chameleon or Transfusion. They tried this, but their image quality just wasn't as good as the dedicated generators.
That's the risk, yeah. They tended to be biased toward the understanding side. The field sort of accepted the complexity of decoupled models because it seemed like unification meant you had to sacrifice fidelity.
And Tuna's breakthrough was figuring out how to get that deep fusion without sacrificing quality.
That's the architectural genius of it.
But let's get into that.
Yeah.
They looked at the best practices, right? Autoregressive text for understanding and latent diffusion flow matching, specifically for generation. But the key choice was the visual space itself.
Yes, and this is really key. They anchor the entire system in continuous VAE latents. We know that these continuous latent spaces just give you higher fidelity images and video compared to older methods that used discrete visual tokens.
Because the discrete tokens lose information when they're quantized, which hurts the final image quality.
Right. By starting with the VAE latent space as the foundation, Tuna basically secures that high-fidelity generation right from the beginning.
Okay, but if the foundation is VAE Latents, which are designed for pixels, how do you inject that high-level semantic intelligence you need for, complex reasoning?
And that's where the cascade comes in. So the VAE encoder does its job first. It does 16x spatial and 4x temporal downsampling and produces this clean latent, which they call 6$R.
And then, instead of having the big representation encoder, the SigLIP2, look at the original image. You force it to look at the VAE's latent space instead.
Precisely. They use the strong SigLIP2 encoder, but they have to modify it. Because the VAE has already downsampled the image 16 times, the SigLIP encoder can't use its normal 16 by 16 patch embedding layer.
The sequence length would be all wrong.
Exactly. So they replace it with this super lightweight, randomly initialized 1x1 patch embedding layer.
That's fascinating. So you're basically forcing the semantic encoder to operate at the same resolution as the generation space.
It's a very elegant trick. It makes the representation encoder extract those semantic features directly from the compressed VAE latents. This is that deep, early feature fusion we were talking about.
And what happens to those tokens?
They pass through a simple 2-layer MLP connector and become the final unified representation sockers. And that's what the LLM decoder uses for absolutely everything.
That sounds so much cleaner than having two separate feature streams that the LLM has to somehow negotiate.
It is. The system is inherently unified end-to-end. The representation, autoregressive, is used for understanding tasks when you feed it a clean latent, and it's used for generation when you feed it a noisy latent for the flow matching process.
And what about video? That temporal dimension usually causes massive headaches, right? Exploding sequence lengths, training costs.
Yeah, they avoided the obvious and very expensive solution of just flattening all the frames into one giant sequence. Instead, they use a pretty clever trick with window-based attention.
How does that work?
They just reshape the frame dimension into the batch dimension when they process the input. This lets their modified encoder operate on these manageable 4-frame windows independently. It's super efficient, but you don't lose the temporal coherence.
That kind of structural efficiency is so important.
Yeah.
But to get these results, they needed a pretty strategic 3-stage training process. Why not just train it all end-to-end from the start?
You can't, really. You have all these different components that need to be aligned progressively. You've got a powerful but frozen LLM, you have a generation head, and you have this new modified visual encoder. They can't all just learn optimal features at the same time without some guidance.
So stage 1 is about building that visual foundation first.
Precisely. In stage 1, the LLM decoder is completely frozen. The focus is all on training the representation encoder and the flow matching head. And they do this using both image captioning and text-to-image generation objectives.
And that combination is strategic, I'm guessing.
Very. Image captioning gives you that rich semantic understanding, kind of like contrastive learning. But the generation objective is the really critical part here.
Why is that so vital in stage 1?
Because it forces the gradients to flow all the way back through the visual pipeline. It ensures the representation encoder is aligned for high-fidelity generation before you even unfreeze the LLM. It stops the model from developing that semantic-only bias we saw in older models.
Got it. And then stage 2 is where the LLM gets to start learning.
Yep. In stage 2, they unfreeze the LLM decoder and continue pre-training. They also ramp up the complexity, adding instruction following, image editing, and video captioning datasets.
So it's bridging that gap from raw features to higher level reasoning.
Exactly. And stage 3 is just the final polish. It's supervised fine-tuning, or SFT, with high-quality instruction data and a really low learning rate to keep things stable.
And just a quick note for you listening, the 7 billion parameter version was trained without video data just because of the huge cost, but the results on still images are still incredibly compelling.
Absolutely compelling. For multimodal understanding, the 7B Tuna doesn't just compete with other UMMs. Hitting 61.2% on MM* puts it in the same league as these massive understanding-only models.
And for generation.
A 0.90 on GenEval is a huge achievement at this scale.
You know, what really sold me on the semantic depth was the text rendering quality. That's usually a huge weak spot for visual models.
It is, and Tuna showed a really clear advantage on the 1IG bench here. That's strong proof. I mean, to render text accurately, you need almost perfect semantic grounding and compositional accuracy.
It confirms the model actually understands the prompt. It's not just generating pretty noise.
And that richness translates directly to complex editing, where it scores a 4.31 on ImEditBench, which is top of its class for UMMs.
Okay, let's talk about the proof. The ablation studies. This is where the team really shows scientifically that their early deep fusion architecture is just fundamentally better.
Right. These ablations were done on the smaller 1.5B model to keep costs down, but they confirm everything. First, they compared the native Tuna architecture against a truly decoupled setup.
Yeah.
Unification wins, period, across every single metric. It just confirms that having fewer representation conflicts leads to better performance.
But the really big question is synergy, right? Did the two tasks, understanding and generation, help each other, or did they interfere?
The results show undeniable mutual enhancement. The jointly trained model, Model 12, was better at understanding than the understanding-only model, and it was better at generation than the generation-only model.
So that proves it. Joint training reinforces both skills when you have that shared representation.
Exactly.
Okay, now the head-to-head. Tuna's closest competitor was probably Show02, which was also trying to unify things, but with a dual-path late fusion approach. Why didn't that work as well?
Right, so Show02 was designed to merge its features at the very end with a fusion layer. Tuna, on the other hand, forces that fusion to happen deep inside the model, right from the start.
And Tuna consistently performed better.
It did, but the team really wanted to know why. And this is where we get to the CK-NNA score analysis. This is the metric that really explains the architectural failure of late fusion.
Okay, so break down what CK-NNA is.
It measures the correlation or the alignment of a model's internal features against some gold standard reference. They tested alignment against two things: SigLIP2 features, which is the gold standard for semantic understanding, and SD3 medium features, the gold standard for high-quality generation.
And if a model is truly balanced, it should align well with both, shouldn't it?
Absolutely. And both Tuna and Show02 aligned well with the semantic, the SigLIP2 features. That wasn't the problem. The failure point was on the generation side. Tuna showed consistently higher alignment with the SD3 medium generation features.
Which means its representation space was actually balanced for generation quality. And Show02.
It had this really severe semantic bias. When they checked its final fused representation, it correlated really strongly with its understanding branch. A CK-NNA score of 0.45, but it had a terrible correlation with its generation branch.
And what's the score?
Just 0.07. And that's the key takeaway. The late fusion architecture prioritized the understanding path, basically starting the generation path of the signal it needed. Tuna's early fusion prevents that from ever happening.
That is just a phenomenal architectural insight. It really proves that where you put the fusion point is everything. Okay, let's talk about the qualitative results, because the compositional accuracy they got is just visually stunning.
Oh, I love these examples. They go way past simple recognition and get into really complex instruction following. Take the whiteboard example. The prompt was incredibly detailed. It asked for rendered text with a specific underlined phrase and precise placement of items on two different shelves.
Right. It was books and markers on top and a cloth and sanitizer on the bottom.
A huge test of scene understanding, spatial reasoning, and text rendering all at once.
And Tuna nailed it.
It was the only model to get it perfectly. Other models would mess up the text, or they'd get the item placement wrong, putting the sanitizer on the top shelf. This shows real semantic grounding.
And they had some fun with the more imaginative prompts too, didn't they?
They did. The tuna fish wearing a Hawaiian shirt and straw hat underwater example is a classic test of blending these complex, sometimes conflicting concepts.
And Tuna pulled it off.
Perfectly. Rendered the fish with all the right accessories, high fidelity, and kept that consistent underwater feel.
That ability to follow instructions, even implicit ones, also really showed up in the image editing results.
Absolutely. They showed it could do style transfers, like turning a photo of a dog into a claymation figure, and handle abstract instructions, like applying high-end studio lighting from the left to a picture of a doll. The model has to understand not just the object, but the physics of light.
And finally, the video generation. Even from the smaller models, it confirms this whole unification idea isn't just for static images.
Not at all. The results, like that red balloon floating down a cobblestone street, show really smooth motion and high temporal fidelity. It proves that all those efficiency tricks they use for video didn't hurt the final output. The unified space works for temporal tasks, too.
So, to synthesize this whole deep dive, Tuna offers this incredibly elegant and effective solution to the unified multimodal challenge. By anchoring its system on continuous VAE latents and using this cascaded deep fusion architecture, it successfully creates a balanced, singular feature space.
And the ablations provide the proof. They show definitively that early deep fusion promotes that mutual enhancement between understanding and generation. It just makes the model better than the older late fusion or decoupled designs. It really sets a new standard.
Which leaves us with a final thought for you to mull over. If strengthening the visual representation encoder, so going from SigLIP to SigLIP 2, or maybe adding features from something like Dino v3, if that consistently gives you these immediate measurable gains across the board, how close are we really to hitting the ceiling of what current vision foundation models can provide? And does the next massive leap in performance have to come entirely from architecturally superior LLM decoders?
That really is the question facing the field now. And for anyone who wants to see the detailed diagrams, the CKNNA analysis, and all the amazing qualitative examples, you can find the paper and the project page at tuna-ai.org.